So I want to welcome everyone to the final installment of our seminar series for this semester. Today we are lucky to have with us Giacomo De Nicola, who is a postdoctoral fellow at the Harvard T.H. Chan School of Public Health. And he is mentored by Chris Golden of AI-SDM as well as Francesca Dominici. His postdoctoral research is part of the Climate Smart Public Health Project, which aims to understand the impact of climate on public health outcomes. He has a PhD in statistics from LMU Munich, as well as a Master of Science in Economic and Social Sciences. And his talk today focuses on harmful algal blooms and their impacts on public health in Madagascar. So I'm happy to turn it over to you at this point, Giacomo. Looking forward to your talk.
Thanks. Thank you very much, Norm. Really glad to be here. It's an honor. Thank you for inviting me. And again, sorry for not being able to come down there in person, but to whoever will be there, I'll be there in, I think, exactly 3 weeks for the annual meeting. So I'm excited about that and to meet you all in person. So yeah, today I'll be talking about our project, which is a collaboration with a fairly large group here at the Harvard Chan School of Public Health, and also in collaboration with the AI-SDM a program. And it's about studying marine food poisoning as a function of harmful algal blooms and climate in Madagascar. Before I jump into it, since many of you may not know me, as Norm already said, I'm a postdoc at Harvard, where my broad area of expertise is applied statistics for public health and society. I started here about 8 months ago, so still fairly new to the US system. Before this, I did my studies in Europe. I did my PhD in statistics in Munich, and before that, I studied statistics and economics in Italy. So, Norm already mentioned this work is part of the broader framework of climate smart public health. What is this fancy word meaning? Well, it's kind of a framework which was kind of conceptualized by my postdoc mentor, Chris Golden, who is also a co-PI in the AI-SDM program, as well as Francesca Dominici, my other postdoctoral advisor. And the idea here is that climate smart public health is a framework for enabling adaptation and resilience by integrating comprehensive assessment and monitoring systems to detect climate sensitive health conditions early and respond effectively. So it's really about adapting and reacting to climate threats and extreme weather events, such as heat waves, cyclones, floodings, and harmful algal blooms, to enhance emergency preparedness and be able to kind of prevent and react to some of the damage that these climate-related stressors inflict on populations. And kind of the pilot project for this is Madagascar, where this study is also based. And one of the reasons why Madagascar is a prime candidate is because it's one of the countries in which climate is doing the most damage. Madagascar is the first country in which climate change-induced famine was declared. It's very sensitive to cyclones, floodings, as well as other. It's very, very hot, so any kind of increased heat also does a lot of damage. Therefore, it is a unfortunate prime candidate for this climate smart public health ideas. Now let's get into it. So you probably all know what the images on the screen represent. These are all examples of harmful algal blooms. So some of them are at sea, some of them are in freshwater, some of them are green, some of them are red. Notoriously, the red tides in Florida make the news very frequently. And what are harmful algal blooms? Well, harmful algal blooms can simply be defined as algal mass that spun out of control. They are simply too large and therefore cause damage to the ecosystem or to humans in one way or another. I say one way or another because algal blooms can be harmful in several different ways. For example, just by being too large, they can create imbalances in the ecosystem. But one way in which they're notoriously potentially damaging is because they can also become toxic. And if there's large blooms of toxic algae, this endangers both the wildlife as well as humans. And this is a picture of how this mechanism can look like in practice. So increased particular kind of conditions, including increased heat or very hot weather in general, as well as agricultural industrial runoffs, can lead to increases in algae and create harmful algal blooms. These harmful algal blooms consist mainly of phytoplankton, which then go up the food chain because they get eaten by zooplankton and or small fish, as well as shellfish. Then the small fish gets eaten by the large fish, which is then captured by humans, which then consume the fish and get poisoned by these toxins. And these toxins are toxins that are present in nature, but pretty serious. Like, for example, ciguatera toxin is a very famous one, which leads to very serious neurological symptoms. Another frequent toxin is cyanotoxin. So this is the same as cyanide. So extremely dangerous and toxic. So this is kind of the main kind of pathway to intoxication that we're now studying. And the outcome of interest here is severe marine food poisoning. And from now on, in short, will be MFP. Now, what is precisely MFP? Well, local practitioners in Madagascar, they diagnose it if there's a combination of strong vomit, strong diarrhea, fever, and neurological symptoms. So you need at least 3 of those 4 to be diagnosed. So it's a very kind of composite diagnosis and very specific. Plus, you have to have eaten fish before the onset of symptoms. And most often, these cases of marine food poisoning happen in connection with other individuals who are experiencing it similarly. So the idea here is that if you ate the same fish as the rest of your family, for example, you're supposed to all experience a varying degree of the same symptoms, and this will lead to a more higher certainty in diagnosing the food poisoning. And these poisonings are often connected with toxins, as I said, stemming from the harmful algal blooms. Of course, these symptoms could be coming from a very severe case of a different type of poisoning, but especially the neurological symptoms are most frequently associated with the toxins from the HABs. HABs is short for harmful algal blooms, of course. And these cases are often, they can be mild, but they're often pretty serious, and they can lead to long-term consequences and even death, unfortunately. And this phenomenon is a pretty large scale in Madagascar. Every year there are thousands of reported cases of very severe marine food poisoning. And given how the healthcare system in Madagascar works, and given how underdeveloped the country is compared to what we're used to, there are very, very likely tens of thousands and perhaps hundreds of thousands of undiagnosed and unreported cases, because many people simply don't really go to the clinic. There's no clinic in the vicinity, or they just prefer to treat their symptoms at home or in their communities. And the problem is, of course, very well known to the local authorities. In fact, this project is in collaboration with the Ministry of Fisheries and the Blue Economy. The minister is a co-author on this paper. He was actually supposed to come to Harvard next week, but unfortunately there was some civil unrest in Madagascar, and that he was forced to cancel the trip last minute. But this is very much collaboration work, and they're very interested in where this goes, because currently they only have a very broad and non-targeted warning systems for this. So these kind of two signs, which are usually distributed through the internet and social media, they give a blanket warning for either the whole season, the whole hot season, which is 6 months out of 12, or for the full year. They're in the Malagasy local language. And they say, don't eat this fish for the whole hot season, or don't eat this fish ever, or be careful when eating this fish ever. Which, of course, is not very reasonable, because a very, very large percentage of the Malagasy population, especially on the coast, which is a large part of the Malagasy population, given that it's an island, they depend on fish for their lives and livelihood, and they don't really have the option to eat other types of food. So these warnings are so broad and so untargeted. They go for the whole country, for the whole year, for the half of the year, which pretty much go unnoticed. I tried to go on the Facebook pages of the ministry, and most of the reactions are laughing, because people can't really afford to follow these. And so, what research questions do we want to answer with this study? Well, first of all, what are the environmental drivers of marine food poisoning events? What's associated, what's causing, and what's associated more in general with these food poisonings? And narrowing it down, what role do specifically harmful algal blooms play in this? And finally, can remote sensing help in predicting, or at least narrowing down, the scope of HABs in order to ultimately prevent some of the marine food poisoning events that actually happen in Madagascar? And by the way, I didn't really say this before, but feel free to interrupt me at any point if you have any questions or doubts. Of course, there will be room at the end for questions, but feel free to interrupt if you have something that you would like to be clarified. Okay, so now we talked about our primary kind of outcome of interest. Let's talk about the data here. So we are using data that is given to us directly from several ministries of Madagascar. It's a very fine and granular data coming from every single clinic in Madagascar. There are a total of about 2,700 clinics in Madagascar, and each of them is associated with a catchment area. Here you see a map of basically the area that each clinic covers. And every person, the assumption is that every person in this area, for example, goes to the same clinic. And of course, the area for each clinic varies. There are areas in which the population is more dense, like the capital here. You see, it's very hard to distinguish the borders, because there are millions and millions of people, and therefore there's a very large number of clinics. And there are areas like here, which are super rural and very low population density. Therefore, the clinic catchment area is 100 or more square kilometers, which makes it tough to get to the clinic itself. And the data goes from 2010 onward overall, but for marine food poisoning, they started tracking it at the end of 2015. So the data that we'll analyze starts from the beginning of 2016 and onward. And these are basically cover all the public facilities. Some of them are small clinics, some of them are more closer to hospitals, and they're defined as CSB1 for the smaller one and CSB2 for the bigger ones. Of course, with the data set like this, there are many challenges. Clinics sometimes move, sometimes shut down. There's new clinics opening over time. They're not that easy to geolocate and to define these health sheds. Um, Also, the things that they tracked and the way that they track them changed several times over the years. Every year there's something different. So it's a big ask. It's a big kind of task already to clean this data set and have it into a coherent set of data that is possible to analyze. But luckily, our team has had, at least so far, enough resources to be able to do this. So we were able to harmonize these data over the years. And here you see a first visualization. This is a very raw for now. So this is just the number of total marine food poisoning cases. But actually, we're not going to focus on the cases. We're going to focus on the number of marine food poisoning events per month. So what's the difference between a case and an event? Well, a case is a person that suffered from marine food poisoning, while an event is a set of people in the same clinic in the same month that suffered from marine food poisoning events. And the assumption here is that the data is sparse enough such that we can treat a set of cases that happened in the same small clinic and the same month as a single event, because what we're interested in will be tracking down the connection between algal blooms and marine food poisoning events. Therefore, it doesn't really matter how many people were sitting at the table. What matters here is how many kind of events of algal blooms causing food poisoning there were. Yes, Norm, you have a question?
Yeah, I just had a really quick, pretty basic question. So I think you may have alluded to this earlier, but when you're looking at these symptoms, is it purely just like the symptoms that you defined? There was like a neurological one and a gastrointestinal one or something, right? Or is there something where it does get marked like in the clinical notes, like, oh, this person like ate like this type of fish or something, or is it purely based on like symptoms?
No, 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 no. It's also connected with the so if they didn't eat fish, they're not gonna get hit with this diagnosis. So it's very, very
Okay,
specific. We
it's a
don't
really
get the type
specific.
of fish, unfortunately. So we only get the number reported of the diagnosed people. But the diagnosis, we've talked to several local practitioners, is made, this specific type of diagnosis is made in connection with eating fish. And when there is reasonable suspicion that is the fish that caused
Got it. Great.
otherwise it's classified as a general food poisoning or a diarrhea or another thing, which are actually much, much more frequent
Okay.
events.
Thanks.
Thanks for the question. All right, so we're going to be focusing on these marine food poisoning events. And as you can see here, it already appears that the events are not kind of evenly distributed over the island. First of all, there's many more on the coasts, which is very natural, given that fish is eaten much more on the coast than in the inside. Also because roads are not as developed as they are, as say, in Europe or in the United States, and transportation is costly and difficult in many cases. Plus, coastal communities are the ones that, as a result, also historically are more dependent on fish and eat more fish. But also, there's some hotspots. You see the northwest here and the south, sorry, yeah, northwest and the southwest. And in general, all of the west coast. I mean, this area is super low population density, we'll see later, but all of the west coast. And this, we will see this is not a coincidence. And this kind of gives me a nice segue into our key exposure, namely HABs data. So ideally, to track HABs, we would have a combination of local reports and water samples and analysis, as well as pictures. And this is where it is for the US. There are kind of well-established systems for tracking HABs and with like modern warning systems. But for Madagascar, there is nothing of the sort. So we have to completely rely on satellite data for now. And satellite data Luckily, there are really good satellites that work at a global scale. Therefore, they're able to track Madagascar just as well as any other place. And what these satellites are able to do is they take very frequent pictures, which are then analyzed by algorithms and climate centers to kind of give out and provide a number which represents the chlorophyll A, the estimated chlorophyll A level, which can be used and is widely used in the literature as a proxy for algal activity. So a larger chlorophyll A level will indicate more algae. And it boils down really to the color of the water. So these are algorithms that are based on the color of the water. And so we're using, there's a few different options for this type of data. We are using data from the Copernicus Marine Service, which provides data at the 4x4 kilometer resolution, so it's pretty fine grained. And as I said, they already pre-process the photos and give out the chlorophyll A number, which is pretty awesome. And we're going to use monthly aggregated data, as that is the outcome, also the resolution of our outcome as well. So it's really natural to just use monthly chlorophyll since we have monthly cases. And so this is a map of the average chlorophyll A concentration around Madagascar. So what do we notice? Well, first thing that we notice for sure is the fact that it's very much more concentrated on the coasts. So the color farther away from the coast, I don't even show it here in the ocean, but in the ocean it will be completely dark and close to zero. While the coasts are the brighter color and therefore the higher chlorophyll concentration. And especially here, this area on the west coast is much more active in terms of chlorophyll, which is also explains partially, at least why there were also many more marine food poisoning cases there, despite it being lower population density than the East Coast. And now we come to one of our main challenges here on the data side, which is, okay, our exposure chlorophyll is measured at sea, while our outcome, marine food poisoning, happens on land. So how are we gonna match those two? We're gonna basically have to assign to each health shed, each catchment area, each clinic, a certain level of exposure, right? And so there are many different ways to do this. What we're doing here is we're gonna create a buffer area around the coast, just like this. And we chose to do a buffer of 50 kilometers because 50 kilometers is kind of a reasonable range for many of the fish species. So this was through kind of domain expert. Many of the fish species are coastal, they're reef species, and therefore they don't have a very large range. So 50 kilometers is kind of the maximum range that they roam around the coast. And then once we look at this 50 kilometers radius, we can say, okay, we take the maximum pixel of chlorophyll, so the maximum level in a single pixel within this 50 kilometers radius, and we assign this to the catchment area. Because why the maximum? Well, first of all, the average would be very, very sensitive to the radius. So if we choose a larger radius, we'll have lower numbers and we'll just dilute all the data. The maximum is because we're interested in a single bloom in the area. So we want to see kind of what's the more severe level of algal mass that is close to the health shed in which the fish is then caught. So that's what we're doing here. That's what I just described. And if we do that, we go from this, which maps kind of the coastal chlorophyll, over to this, which is now inland, I mean, coastal health sheds matched to specific levels of chlorophyll, given basically using these So you can see that this also reflects the fact that, and here it's even more visible, how higher the levels of chlorophyll here are here on the west as opposed to the east. And the reason is pretty simple. Madagascar is very diverse, first of all, in terms of climate in general. And we'll talk about more in a second, but also especially the coasts. Here, it's open ocean. It's very fast water and fairly cold. And there are a lot of currents. So it's not that easy for algal mass to form and stay in place. Well, this area here is tropical climate, and it's the Mozambique Channel, and it's pretty shallow here. And there's a big reef. Well, here there is no reef. Here it's just open water. Well, here it's reefs, and it's calm and it's warm. So mangrove area as well. So all of this just to say that, well, we have a much more ripe environment for HABs to form here, and you see this in the chlorophyll levels. And if you see them side by side, you also see kind of a clear connection between the events and the chlorophyll A levels for each hell shed. Okay, so now we defined our main exposure and our outcome, but there are also other things that we are going to try to measure the impact of and or control for in the analysis. First of all, I'm showing here a wealth index. This is something that is provided by one of our collaborators at the World Bank. So this defines the wealth, and it's matched also at the health shed level. So this provides the wealth index for the different health sheds. And we can see a clear pattern here. This is the capital, and this is by far the wealthiest area in the country, and everything that is around there is also darker, meaning wealthier, while there are some areas, especially on the west, that are much less developed and poor. And this is also very much correlated with population density by health shed. So you can see that the capital is also, as is classic, the most dense area and the wealthier, while these areas are much lower population density. Here we're on the log scale, so the differences are pretty stark. And given that these two are so correlated, and given that the wealth index is actually also utilizing population density, we're only going to use the wealth index in the model. We're not going to use population density. We're going to use population and wealth index, therefore, we're not going to include population density as well. And then here, I was talking about the climate before. This is average temperature by health shed on the surface, 2 meters from the surface. And you can see also very stark difference. So Madagascar has 4 broad macroclimates. It's a relatively small area. It's the size of France. But it has both a arid desert climate in the southwest here. It has a tropical here, rainforest here, and temperate climate here. So these are 4 macroclimates, and obviously there's a lot of subclimates within that. So you can imagine, and you can see that there are huge differences in temperature, average temperature. I mean, in Celsius, 27.5 degrees Celsius is extremely hot climate if you take the average over the year, day and night. It's very extreme, and you have stuff that is less than 10 degrees than that, and that's around the capital, which are, by the way, mountains. Same goes for precipitation. So you have this very arid area here on the southwest, and you have rainforest near the equator with heavy rain, and you have also this tropical area in between. Sea surface temperature, also, I already talked about it here, much warmer water on the northwest. The south is kind of the coldest, and southeast in general, it's more open water, colder, faster currents. And again, here I'm showing them side by side with the average chlorophyll levels by health shed. And you can see that there's a very strong correlation between the two. And this is actually, the correlation goes both ways, because in fact, sea surface temperature is not just causing more algal blooms, but it's also an indicator of algal blooms, because when there are lots of algae on the surface, what you get is that the surface heats up. The sun is able to heat it up much more. It absorbs more of the heat, and therefore the measured sea surface temperature will also be higher. Therefore, these two things are two main indicators of algal blooms. So it's not just a cause relationship, but it's also an indicator of the phenomenon itself, the sea surface temperature. Okay, now that we have defined all of our components, we can look into the model, and we're going to use a variant of a generalized additive model. So this is basically a generalized regression model which allows for the inclusion of nonlinear effects to be able to have more data-driven estimation results. And in our case, we have a binary outcome. We have, in a given month and year, and hellshed, was there or was there not an algal bloom event? So we're going to use a natural choice logistic regression. And then our key exposures of interest, in particular chlorophyll, as well as other climate variables, they're going to be modeled with smooth effects. So we're not going to assume linearity a priori. We're not going to assume that the effect is linear in the log odds of the response, but we're going to let the data speak, so to say more. And I'm going to show you a bit more of what that means in a second. And we're using P-splines for estimating smooth effects. It's a bit of a more technical side, and they ensure more balance between flexibility and smoothness. Happy to talk about this more if there's time and curiosity later. Okay, so the other big challenge that we face is the fact that some of our key exposures, like sea surface temperature and chlorophyll, are marine. So even if you do match them to hellsheds on the coast, you're never going to be able to match them to what happens inland. We don't have chlorophyll A levels or sea surface temperature levels for the capital. This would make very little sense to try to attribute them just by using a nearest neighbor approach. It wouldn't make any sense. So what are we going to do? Are we going to just throw away all the data that is in the middle? This was our initial idea, but this is problematic because we're throwing away a lot of data, first of all, so losing a lot of power. And second of all, we're interested in studying marine food poisonings in general, not just in coastal areas. Sure, our main interest is in measuring the effect of harmful algal blooms, which is purely coastal, but it would be good to get insight also on what is associated with marine food poisonings inland. And so we don't want to do that. And the solution that we found is kind of a statistical trick. So first of all, we're going to create a binary variable, coastal, which is going to be 1 for coastal hellsheds, so all these hellsheds, and it's going to be 0 otherwise. And then we're not going to include in the model, we're not going to include the main effect of chlorophyll and sea surface temperature, but we're only going to include the interaction between these coastal variables, so 0 or 1, with the chlorophyll and the sea surface temperature, which means that this effect only comes into play into the model for coastal areas. And it's forced to be 0 otherwise. So we're not forcing the chlorophyll level setting the chlorophyll level to 0. This is it's subtle but important distinction. We're not setting the chlorophyll level to 0. This would be very kind of improper from a statistical perspective to set a chlorophyll level of 0, but we're forcing the effect of chlorophyll to be null. So the effect of chlorophyll only comes into play into the model for the coastal areas. This way we're able to disaggregate also the effect of a place being coastal when its chlorophyll is 0, with the effect of the added chlorophyll on the coastal area. So this is kind of taking two birds with one stone. So this is just the formula in R. So just to show you, basically, we're estimating the smooth effect of this interaction between this coastal variable, which is either always 0 or 1. So it's either this is in the model or not in the model for coastal or non-coastal areas. And then we have the month of the year to check for seasonality. We have a smooth time trend. We have the wealth index, the population, whether or not the clinic is a hospital or a small clinic, the land temperature, the level of precipitation, and the sea surface temperature, including the same way as the chlorophyll. And as for the results, let's jump straight to our key exposure. So we can see that these are the smooth effects. So we're gonna talk about them in a second by showing the plot. But we can see that chlorophyll does have a statistically significant effect as well as precipitation. But first, let's focus on the linear exposure. So we can see that the sea surface temperature has a pretty strong positive effect. So for every increased degree Celsius in the average sea surface temperature, there's an increase in the log odds of 0.13, which is pretty large. So if you go from the coldest sea areas to the hottest sea areas, controlling for all the other factors, you have a pretty large jump in the expected probability of a marine food poisoning event. A bit smaller is the effect of land surface temperature, but still significant. There are definitely more cases diagnosed in the larger clinics, given that this diagnosis is pretty kind of specialized. And interestingly enough, wealth index has a positive effect, which also probably is an indication of the fact that the diagnosis is kind of a tougher one and it's easier to diagnose. And people will also tend to go more to the clinic in these areas. So this is something that we always have to deal with. The data is not kind of exactly representative because there is different propensities and the clinics work in different ways if you're in the capital or if you're in a rural area. And finally, also interesting to see that the effect of a place being coastal, assuming a chlorophyll level of 0, does not substantially differ from a non-coastal area. So the effect of being coastal itself does not really lead to a higher likelihood of marine food poisoning events if we assume that the chlorophyll level is 0. Now let's go to our key exposure, the chlorophyll itself. And this is quite interesting. We see that there's a pretty strong linear effect, and this is linear in the log odds, right? So it's a very strong effect for increasing levels of chlorophyll up to 10 milligrams per liter of chlorophyll. Then the effect tends to stagnate, disappear, or perhaps even slightly go down, although I would not overinterpret this going down because then the data gets super rare here. And so we lose all the power, and this is not anymore kind of statistically significant. Would make sense actually to have a slightly decreasing for the very, very, very high chlorophyll values. I mean, everything above 10 is considered very extreme and visible to the naked eye. So people do know that it's not healthy to eat fish when there is tons of algae in the water. Therefore, we could see there being a protective effect. We see this often in environmental health applications. For example, when there is very, very high level of PM 2.5, when there's a wildfire going on, people don't really go out of the house because they know it's bad for them. Well, when the level is high, but not quite high enough to prevent people from going out, that's where you see the worst public health consequences happen. And I learned this by talking to a lot of environmental health experts. There are a few who are also part of the project. But yeah, so the key takeaway here is definitely the fact that there is a strong and statistically significant positive and increasing effect of chlorophyll in the kind of normal range. And precipitation, also we see that there's a few more events in the dry area, the very dry area, and then the effect kind of bottoms out and doesn't really change anymore after a certain level. Now, what I'm showing here is kind of a control model. We applied the very same exact model to instead of using marine food poisoning, we used non-marine food poisoning. So the general food poisoning, which are not classified as marine. And here we definitely would expect no effect of chlorophyll. And we were very happy to see that that's what we see in the data. So this was kind of for us as a control to confirm that we were not looking at some noise and getting some kind of fake results. But in fact, this really kind of shows that the chlorophyll has an impact. Most likely this is a real impact on marine food poisoning because it doesn't appear to be the case. But for example, precipitation, dry areas have the exact same impact on marine and non-marine, which means that this is not part of the kind of algal bloom effect. And this is we're happy to have this in as a control, but we should interpret this as specific to the marine food poisoning events. Okay, so I see that I'm close to time, so just a few more minutes of discussion and conclusions. What have we learned? What are we learning? What have we learned with this study, which is not yet published, but is kind of in the writing stage. Therefore, feedback and suggestions are very welcome. So, in general, very little is known about harmful algal blooms and their impact in Madagascar, and more generally in Africa and tropical and low income settings. There are really good studies. There are beginning to be really good studies for the United States, as well as some places in China. But we know very little about Africa and in general low income countries. And no population studies on marine food poisonings exist, at least certainly not in Madagascar. So this is already kind of a first step in that direction. And from the study, we can clearly see that there is an impact of remotely sensed algal blooms on marine food poisoning. So there's a strong positive effect of both chlorophyll and sea surface temperature, which are combined to be our combined indicator of harmful algal blooms and algal bloom activity in general. Of course, this is only about diagnosed cases. As we talked about, there's a huge rate of underreporting. Nonetheless, this data is still very, very rare for a setting as Madagascar, one of the poorest countries in the world. At the moment, it's basically the poorest country in Africa. So this goes to say a lot. And these data are very difficult to obtain, this level of granularity. And one thing that we learned for sure is also that remote sensing can help in kind of adapting and responding to harmful algae by detecting them. And this is especially important and useful in settings where in situ monitoring and analysis are hard to do because it would be economically not really feasible and practically not really feasible. And as a result of this, we also have more work in preparation, and this is actually in collaboration with a talented team of students over there at CMU within the AI-SDM Masters. Some of them are also here in the audience. And the goal of this work is to actually create an early warning system for detecting harmful algal blooms using remote sensing data in order to deliver better warnings than the general blanket ones that are given now, and to prevent some of these marine food intoxications. So that's it on my side. Thank you all for your attention. And as I said, very open to questions, comments, and suggestions.
And feel free to just unmute We have a fairly manageable group here, so feel free to just unmute with any questions. I do have a quick question to sort of start things off. I know that you're collaborating across organizations within AI-SDM. Can you talk a little bit about, like, I know you're working with CMU because we had Sarvesh, a master's student here at CMU, give a talk as part of an event recently. So we heard a little bit about that work, but um, maybe for this group, could you sort of fill in the blanks on what institutions you're working with, if it's just CMU within AI-SDM, and kind of how they're contributing to this as well?
Yes, so this group is very interdisciplinary. For this specific project that I presented, it's mostly Harvard-based, although it spans different departments. So there's the Department of people from the Department of Nutrition, the Harvard Data Science Initiative, Department of Biostatistics, and the Department of Environmental Health are all involved. And the other project is in collaboration with CMU, as well as another postdoc that is from Berkeley, who is also here, or partly from Harvard and partly from Berkeley. And there's also a researcher, actually, yes, there is a researcher from Berlin also in both projects, that is involved in both projects from the Charité, who is also a public health expert. So it's fairly interdisciplinary, as you can see.
Do you know like what the student at CMU, kind of what their piece of this is, or if they're working on like related work, just like generally like what's going on?
So they're not involved in the project I presented. They're involved in the like future work that I was just talking about, in the planned and present work that I was talking about, the detection, and they're working on the implementation side. So they're really doing all the kind of methods, research on the models to use, and they're also working on developing a dashboard for doing these early warnings and visualizing the different variables. So it's very, very cool work. It's still in the making, and we'll need a bit more time, but hopefully we'll be able to deliver and show you all the results. And the final goal is to put this directly in the hands of the Malagasy government and the Minister of Fisheries and the Blue Economy, so that they're very much involved in this. And obviously that's exciting because oftentimes this type of research just ends up on a shelf. But this will definitely not be the case for this. But whatever we're going to accomplish, that's going to be implemented.
I'm going to invite Marie to ask her question here to the group. Good to see you again, Marie.
Yeah,
Hey,
nice to
Marie.
see you. And thanks, Giacomo, for your presentation. Yeah, I know that we discussed this a bit, but I was wondering whether you could comment on the feasibility of replicating your study, either separately, in different locations, or actually jointly, and having maybe like some sort of like country specific effect in your models in other places like Bangladesh, or in the Arab Gulf, or in Florida. And I do see the value of the clinical data that you have, but I was wondering whether there's a way to like separate the access to clinical data versus all the work you've done with satellite images, to yeah like run these like exposure outcome relationship models more broadly worldwide.
Yeah, no, thanks for the question. That's a good one. So what this initial pilot study is doing is trying to kind of quantify the relationship between the algal blooms and the observed marine food poisoning events in a setting in which there is no public health warning system for this specific issue. And in this sense, this is a quite unique setting because you have access to high resolution data in kind of an unadulterated setting. At the same time, once this connection is established and quantified, all you need really is satellite data. So we're not going to be any more dependent on the clinic data to build these systems for other countries. And this is kind of the idea of climate smart public health, is that you have these settings. We have Madagascar. We now recently also starting to work on Nepal. Obviously, nothing marine is going to happen in Nepal because there is no coast, but there are many other interesting climate things to study there. And the effect is to then scale it up. The idea is then to scale it up to many other countries. And when satellite data is involved, this is the easiest because we have really global satellites that are constant. Of course, there are also some challenges to this because the HAB indicators vary, as you know, depending on the location. So a chlorophyll level that is a HAB in Madagascar is not necessarily the same level for Florida, because in Florida there is, for example, Carina brevis, which is a species which causes these red tides, which have extremely high chlorophyll footprint. Madagascar, completely different climate. There are no Carina brevis. There's mostly Ostreopsis and other species. But for sure, some of this, at least the methodology, is definitely scalable to other settings with a few kind of adjustments and localization tricks, basically.
Yeah, no, that's very interesting. I mean, kind of along the question that Norm asked, I was wondering whether almost building upon, the statistical framework you've built, whether there's an opportunity for like a student to actually try and scale your work, because now there's a lot of engineering involved, right? If you want to scale that to other coastal places around the globe. But that's really like, I would view it as an engineering effort to scale the methodology you've developed. And then while doing so, of course, like there will be kind of data transfer or like distribution shift problems like those you mentioned. But that could be an interesting like avenue to pursue while also building the I guess prediction or detection tool that Madison's or Vetch team are working on.
Yeah, that's very interesting. I think once this work is published, we'll definitely look into ways of exporting this to similar settings in which there is no real system in place apart from available satellite data.
Yeah. And the reason why I'm mentioning it is if you need another place where you would have clinical info available in order to define your outcome well and, kind of build your models in two distinct places separately, and then, compare the results, then Maya has worked a lot with the public health agency in Bangladesh. So like that could be another place. I was just trying to think like of other places where you would want to do exactly the same thing. The outcomes might not be coded exactly the same way, but like you show evidence that the two models corroborate each other. And then if you have that type of evidence, I guess you'd, like to your point, you don't really need then your clinical data anymore, because like you have shown that the two places exhibit the same shape of the relationship. So you just need to like inform the population accordingly.
Yeah, no, let's keep in touch on this. This could be
Yeah. Sorry, I'll
an
let
interesting
others ask questions.
future step. No, yeah, no, really, thank you. Really interesting question and observations.
Any other questions for our speaker? If not, thank you again, Giacomo. Really appreciate your time. Thank you for those who are here today. It was great to have the questions and the attendance.